platform, you need a conduit which can solve your problems. And when you talk about real life problems, they are beyond just specialist. Um, because when you talk about problems which needs to be solved through intelligence, it's beyond specialist, and it's about integration. So there's a lot of integration science which is involved into it. So if you just throw machine learning algorithms, or if you just throw neural networks into the space, and you can't call it AI as such, we'll just see why that is, because you need to organize it in a particular manner where it improves your chances of finding the problem solutions, rather than complicating the issues, and in the end you don't really get the payoffs. So intelligence, the popular notion is it's got something to do with knowledge, and it's beyond knowledge, and so people generally think that if you have knowledge, you have intelligence. But the core definition of intelligence is something what you use when you don't know what to do. So basically, it applies more in the ignorance and uncertainty space, where you need a certain method of actually dealing with these uncertainties and ignorance. So Jean Piaget was the father of cognitive science, and this is what is the term which was given to him. I mean, he had given. And John Piaget is the father of modern education system. So everything that we are learning and everything we are actually using springs out from these concepts. So let's try and understand what do I mean by saying that it is beyond knowledge. So your environment is actually split into four quadrants. So you have the known knowns, you have the known unknowns, you have unknown unknowns, and unknown knowns. So when you talk about known knowns, so this is what we actually refer to as knowledge. So you already know something, so you know what to do. So you know if you get a fever, you've got to take paracetamol. So it's just connected directly. So you have the knowledge. Maybe you don't know how exactly it works, but you know what to do. So you understand that space. But when you talk about known unknowns, you have I mean, this is a research area. This is a research problem. So we all know that the universe is expanding. So we don't know why it is expanding. Basically, we have the question, but we don't have the answer of. We don't know what to do about it. So, for example, COVID. So we know there is a virus which is killing people, but we don't know what to do about it. So we are in the process of finding an antivirus for it. So that comes into the known unknown space. If you look at the unknown knowns, so there are plenty of things which our body is doing right now. So it's fighting, it's got antibodies, and it's fighting, and it's surviving. We at a certain point, we didn't know how our brain was working. We didn't know how our heart was working. So when the Egyptians actually mummified the body, they took out the brain. They thought brain is just a ventilation device. It is not required. They were more concerned about the heart, because they thought, your intelligence and your thinking process takes place in the heart. So in the mummies, you'll find the heart preserved, but not the brain. So basically, we were using the brain. We were intelligent, but we didn't know that we were using it. So so if you want to relate to a good problem today, you can understand your mother's face, but you really don't know how you are understanding it, right? So that's all encapsulated in the neural network. But when you look at unknown unknowns, there are plenty of things around you which you are just not aware of. So these can be entity specific. So for example, we didn't know how the bats were behaving, how they were navigating space. So those kind of faculties we didn't have, but we are now understanding it through exploration. We are through learning, we are able to find out there are other things beyond what we can see. So we are only seeing a small percentage of our visual, the electromagnetic spectrum. But later on, we found out there is something known as X-ray, there's something known as UV rays, and IR radiation. So all these things we started finding out. So now we understand, we know that 90% of the universe consists of dark matter, and we really don't know what it is. So that is unknown. So we need to explore that. And any process which helps us explore this is what is known as intelligence. So if you look at a small wasp, it is not as intelligent as a human being. It comes inside the house, and then when it's trying to fly out, if the window is closed, it'll go and hit against the mirror and the window pane, and it comes back and it forgets it again, keeps doing that again and again. So there is no learning mechanism. So it is really not able to understand the unknowns around it. So it is not so intelligent. But we as human beings have a specific principle through which we are able to explore this unknown unknowns, and our intelligence has grown from monkeys and we have evolved. Right now we have the prefrontal cortex, which is something which is missing in most of the animals, and that is what gives you this ability to explain things, to understand, because even a lizard can see its prey. So it is using its neural network, and it is using its computer vision, but it doesn't understand what it's exactly doing. The consciousness levels are low. But in a human being, we are able to explain why a particular thing is happening, which actually allows us to build systems. For example, flight. So when you look at a bird, so we've understood the principle. It's based on the knowledge principle, and now we are applying it to all kinds of aircrafts, right? So there are two pillars of AI. Basically, you use rationalism, which is what it entails is you have facts, and now you can mix up facts, and then you can conclude something. So, for example, you've got your clothes outside the house, drying, and suddenly you find there is thunder. So now it's going to rain, and your clothes are going to get wet. So you're not getting any direct data from the clothes that it is getting wet, but these are inferences which you are using, inference mechanisms within a particular rational boundary. So you have facts and you're mixing it up and you're doing that. But sometimes it is not enough, because we thought after the Big Bang the universe will cool down and it will slow down, but the universe was speeding up. So our rationalism told us that the universe is going to slow down, but we through empirism, through data, we found out that the universe is expanding more. So we need empirism too. So where basically we collect data and we try to figure out what is the actual fact. And then we have now discovered there is dark matter, and there's much more than what we actually saw. So these two are a cyclic process. You have empirism going on, your rationalism going on. Let's just have a look at that in the next uh, slide. So you have two processes. You have inductive process and you have deductive process to actually explore your unknown unknowns and use intelligence. And the inductive process moves from specific instance to generalization. So basically from a particular data, so you have given a particular antivirus, you've checked out what is the result, and you do it a number of times, and you do the clinical trials, and then you come up with a fact that, okay, generalization fact that so-and-so vaccine is about 95% effective. So that's generalization. That's an inductive process. It's a data-driven process. And if you look at the components of AI, which actually plugs into this, you have machine learning, which is the broader term. And below machine learning, you have three basic processes. So one is the regression process, where you create the regression curve. So it is basically how one attribute actually affects another attribute, or how one attribute affects plenty of other attributes in a multidimensional space. Classification, clustering is all about one kind of data in a particular cluster. So it can be a 2D cluster or 3D cluster or multidimensional cluster, which belongs to a particular space. And so those can be classified. So for example, you can classify an aircraft and a car. So an aircraft has wings, car doesn't have wings. So there are plenty of attributes through which you can sort of first cluster it, and then when you give a label to it, it becomes classification. So these are the three processes, basic process, which we do in machine learning. And if we use our own brain, so it's human learning. When we use the ICT, it becomes machine learning. So if you look at the other side, the deductive process, you have a knowledge base, and from the knowledge base, you have inference mechanisms. So you can have hard inference. So you can use logic. You can use propositional logic. You can use predicate logic to actually mix up and do logic resolution and come up with the outcomes. That is something like what do you call proving, right? So a formal method in mathematics where you create proofs. And when you look at probabilistic methods, when you have uncertainty, you will be using Bayesian networks. And when you want generative methods, you will be using genetic algorithms and other generative methods which are there. Basically, you are taking facts and you're just mixing it up. And in generation, you can assume a particular fact. You don't know whether it's true or not, but then you put it into the space and then you try to compute. And then you will find whether that fact which you assumed is actually fitting into this environment. Is it a rational thing? Can it work or not? So for example, that is what Elon Musk asked, can the rocket come back and land? And when he put it into the space and did inference, he found no reason why a rocket cannot come back and land. Whereas everybody else was saying it's almost impossible to do it or difficult to do it. And he was able to do it. So deductive process is one, and it's a cyclic process. It keeps moving in a cycle. So when you look at intelligence, there is another aspect to intelligence, which is relative. So intelligence is relative in nature. So if your child opens up a mobile app, in your mobile phone, you will really applaud and say that he or she is so intelligent. But you or me would do it. It wouldn't be intelligent. So what exactly is intelligence? It is relative to the time and space complexity. What that means is it depends on your resource. So if you have less resource and you can produce more better inference, that would be termed as intelligent, rather than you have a supercomputer and after 10 hours you're computing what is 2 into 4, right? Your algorithm is so stupid. So your algorithm needs to be intelligent so that it can evaluate a particular problem and come up with a solution in less amount of time and with less resources. So in computation, it's about storage space, it's about computation space, and it's about the bandwidth requirement in your network. And time, of course, everyone understands. So essentially, we've already talked about how we can relate it to flight. It's the same principle for an aircraft or a bird. And similarly, if you use the same principle for intelligence and apply it on a machine, maybe an Android and maybe a robot, or it can be the internet as such, or a data center, so it can be a huge space. So then it would be the same intelligence. So intelligence doesn't matter. It doesn't matter whether it is biological intelligence or it's in the machines. Intelligence is intelligence. It's a principle and it's relative in nature, and it solves problems and it learns. So this is what we need to understand, and that's why it's not completely related to knowledge, but it's a separate principle. So if you look at our space, we have sorry, I think it's all. So you have something known as intelligence, and you have something known as stupid, right? So a particular process which increases time complexity and space complexity is a stupid process, and a process which reduces it is intelligent. So it's a relative term. Now, when you have these two, if you split your environment in these two, you have human intelligence, which is evolving from monkeys. We've become humans. So our processes are evolving, and we are a portion of us, which is in the intelligent space, a portion of us in the stupid space. But when you look at artificial intelligence, it is the same thing, but it is scaled up. So it is able to understand better, and it is able to preserve that. For a human being, if he understands something after a few months or days, he can forget it. His neural network again can regenerate. But in an artificial intelligence system, you can actually retain that, and it has got the power to actually sift through huge amount of data which we don't have, and that therefore artificial intelligence growing in power. And so some of it is also stupid because as I said, it's data driven. If the data is not good, and if your algorithm is not good, then obviously the results will not be good, which is what we want to avoid by explainable AI. So if you look at now, let's just take a look at our cognitive limitations, right? So if we understand that, then we will better understand what AI is able to do. And also, we would like to know that if AI is able to solve a problem, will we understand how it solved it? Or, if we can understand, why can't we solve it ourselves? So basically, AI is used where we cannot solve, and we cannot be present everywhere. We can't take out a lot of data and consume it. So essentially, AI is something more complex. and it can solve huge amount of problems which we may not be able to understand. This complexity is much more. So therefore, there has to be some way of interface, intelligent or intuitive interface, which needs to be created between the machine and the human being, so that we understand how AI is working in those machines, right? So when you look at our sensors, we've already talked about this. We only see a small extent of the visible, electromagnetic spectrum known as the visible light. And our occipital lobe is a very primitive part of the brain. It was always there in dinosaurs and in lizards as well, and therefore it is found closer to our primitive part of the brain. The other part which is in the front is something new, which is only found in the primates, and our prefrontal cortex is more pronounced only in human beings, not even in Neanderthals. So that is the seat of intelligence. So what happens in the occipital lobe is it is actually through evolution, you have actually gathered some kind of capability to compute whatever data you're getting and then produce results for that. And that's kind of specific. So today you cannot really make out from satellite imagery if a tank is hiding behind under a tree. It may be camouflage. And but an AI system can actually recognize that. So you and me will not be able to recognize with our occipital lobe. We need something else. And also the data which we are taking in is only visible range. Right now we have radars, we have other source of information. So all the source of information, we really cannot process it. Even if you convert it into mechanisms where we can see, convert it into visible range, right? So it becomes difficult to recognize if there is a cancer growing in your body, cancerous cells are growing in your body or not. How do you actually say whether it's malign or is it dangerous? So all of these can be sorted out using machines. And also another issue is we have three different sets of brains, right? It is all evolutionary layers. So you have the reptilian brain, which is the most primitive part of the brain, and it is more reactive in nature, and it actually operates as like a robot. But there is something known as the middle brain, which is the emotional part of the brain, which is also found in primates and animals. So they have some amount of emotion. So emotional part of the brain is a very broad-based system of responding to your surroundings, and it has evolved in a herd kind of situation where your social this thing behavior also matters for your preservation and your existence. But emotional part of the brain, emotions, how it works in the brain is like you have these neurotransmitters which are flooded into the brain, and then it takes a long time for you to actually respond to it. And it may be a wrong thing which may be happening for you. So, for example, if you're going for skydiving and you have to jump out of an aircraft, your mind will be filled with fear and doubt and rage. It can be anything. So you have a term known as amygdala hijack, so which actually relates to this, that if you actually use emotions to compute or to take decisions, it could be bad for you. And because most of the processes in our world are now counterintuitive. Therefore, we need to evaluate using our prefrontal cortex. And for any this thing input, there is always contradictory responses from all these three brains. So when you go for skydiving, your hands will start holding something. Okay, when you jump out, you will hold into a ball, which you're not supposed to do. You're supposed to spread out. And then there is fear, which you need to actually, the emotional brain, which keeps telling you, you shouldn't do it. So you need to suppress that as well. And then you need to work with your prefrontal cortex logically and apply yourself. And to do that, you need a lot of training. So there are other issues like you are using neurotransmitters, which are molecules, which are heavy, whereas, ICT uses electrons, which are fast moving. So the speed is less in our brain. Therefore, the size of the brain is limited. It can't really become big than what it is right now. And then it also deteriorates with age and because of your diet and because of a condition and things like that. So it's not a very good system of really computing. And therefore, you have situations like this where you are seeing a face here, but you also know that it's not a face, but it's coming from the trees and it's just a pattern. So your occipital lobe, which is more prone to seeing faces, is throwing a face at you. But your prefrontal cortex, which is there in the front of the brain, is actually telling you that this is a very funny situation. It is not actually a face. So let's say if you're drunk. So if you're drunk, you're not going to you may be talking to this picture also. So you may really believe what you're seeing because you're not sifting through the prefrontal cortex. If you're afraid or if you're using your emotions and not using a prefrontal cortex, in such situations you will fall prey to these kind of you know hard coded uh, inferences. This is again another example of the same. So essentially every entity has got its own umwelt, its own reality, which is limited in nature. And that's what we need to understand, and that actually creates a problem when we start using complex systems like AI machines and systems. And also that also should give you an intuitive understanding that you cannot be involved in the decision making process any longer, because these are beyond your umwelt, and therefore you need to stay connected. So coming to our the principle of AI, the inductive and deductive process, let's just have a look at what exactly are we using and why it becomes unexplainable at times. So when we're talking about machine learning, okay, so let's try and understand what is noise, what is data, what is information and knowledge. So initially, if you just have some numbers, it's just noise. You don't know what it belongs to. But if you have a understanding of, okay, we are actually collecting information about flats. Let's say 2 BHK flat and 4 BHK flat, and we put it on a particular plane. So that is your data. Now you have a data pertaining to a particular attribute. If you have another data pertaining to another attribute, it's the cost of the flat. And you can use these two data sets and create information. So basically, these are the 2 points where these intersect. So you know that a 2 BHK flat will cost 40 lakh, a 4 BHK flat will cost 80 lakhs, and this is information points, right? So it's informing you about something. But when you actually connect this line and create a continuous, line or a plane in a 3D space, or it can be multi-dimensional place as well, then you are trying to create knowledge. So it's basically telling you that as the flat size increases, the cost also increases, and this is how it increases. There's a slope to it. Now, this is a very simplistic example for you to understand, but essentially, this plane will be multidimensional in nature. It will also be non-linear. So you will not see a very neat line like this. But this is what is regression curve, and this is used to actually store knowledge. So right now, I don't have any information about anything on the line. I just have the line. But now I can predict using this. I can predict that a 3 BHK flat will cost 60 lakhs. So this is a very simplistic thing for you to understand how prediction actually works. You need to generate the space, this line, this knowledge base, and then from there you can start predicting. And in order to really understand that your regression curve or the regression space is actually representing your knowledge, you need to do something known as the null hypothesis testing, which I think anyone who's doing PhD understands that very well. This was not very strict, before World War II, and people were believing in a lot of things. They had their own regression curves and knowledge base. So it was very difficult for us to discern what is true and what is not. But right now, it has to pass through the null hypothesis testing, and then we accept it as the base, knowledge base. So a knowledge space can look like this, very complex. This is in a 3D space, and more than this, you and me cannot even visualize. Machines can actually handle them better. So your brain is actually retaining something like this for every information in this world, and it's computing. And when you look at machines, they have parameters like in millions and lakhs. So that's the kind of dimensions they work in, and we cannot do that. So when it becomes very complex, when it is non-linear, as I said, and when it is multidimensional, you can't do it mathematically. Otherwise, you can sort of calculate the line mathematically. But when you can't do it mathematically, you use neural networks. And this gives you essentially, if you look at this space, a neural network can capture the space. but we cannot create a mathematical formula to capture the space. So neural networks, you have an input layer and you have an output layer, and in between you will have some middle layers, which are hidden layers. So when you give some input, you try and adjust the weights of the connections between the layers, and then try to get an output which actually represents what you are feeding. So if you're feeding a picture of cat, you will actually label it as cat, and if you feed something else, it should not recognize it as cat. So that is the idea, and there you need to come to the conclusion of what kinds of how the weight must be manipulated. So there are mechanisms for that. We will not go into it, but essentially you need to understand that you just feed in the input, and what is the input? Let me just give you an example. If you have a cat's image, so all that is nothing but pixels, and all this pixel is linearized. I mean, it is just flattened, and that is fed into the system as inputs, right? And that is all you do, and then the weights in between, they adjust by themselves. So you have back propagation algorithm, you have forward algorithm, which was used before. Right now everyone uses back propagation algorithm. Then you have gradient descent and things like that, which optimizes these weights, and comes to the best optimal solution, which represents the cat. So you will have an output, let's say 1101, just an example. Here in this example, you have an output for pedestrian, you have 1000. For car, you have 0100, so on and so forth. That's the output in the layer 4. And what's happening in between is taken care by an automated system. So nobody can actually say what kind of weights will come up here and why it is happening. So it's all data driven. If your data, like if you wanted to recognize cats, if you're feeding in cats, it's good. But if you're feeding in a dog's image and saying it's cat, it'll really get corrupted. So what kind of data are you feeding in? It has to be clean, it has to be accurate and represent that integrity must be there in the data. Then your system will be good. Otherwise, if I'm a malicious player and if you're trying to recognize something, I can feed in something in your system continuously, and that system can learn that, and tomorrow it'll identify. These kind of things happened with Google also, right? It identified a Negro as a monkey or something like that. So you need it is still needs to correct itself. You will have false positive, false negatives, which it has to correct itself using the inference engine, which is the deductive process. So so this should give you an intuitive understanding that how things can become dangerous if you just use neural networks. And when you so let's just talk about deep neural networks. If you have more neurons in this, more layers, it becomes deep neural network, and that's known as deep learning. And then you have CNNs and you have LSTM. So these are all some kind of algorithms or models for deep learning models. So essentially, it's just the power of neural network, and this is the same in our brain. There could be slight difference because we are using neural instead of just zeros and one. It's almost the same, and so the power of machines will go up now. So when you look at the difference, the detectives, how do you to actually get contextual queries and information? He's got inference. For example, if I have to the area for, I will have to money from Canada or abroad. How much GST will I have to pay? Can I actually go and work with data in Europe without GDPR? So all kinds of querying, you can start doing it from the knowledge base if you have an inference engine. Again, when such kind of thing is happening, one would like to know what is the reason why that machine is giving me this advice or recommendation. So it should not happen that it's going wrong. So you need to understand also. So if I'm saying should I carry an umbrella when I go to Nandi Hills, so it will have to actually tell me yes. I mean it's going to rain. The weather is bad, but in Nandi Hills, I mean everything is covered, so you don't have to carry something your umbrella. So it can actually give you an explanation because you need to understand why it is also telling you. Otherwise, you will not understand that properly. And also it gives you this thing of uncertainty. So you will use Bayesian networks and others to do the inference part of it. So, okay, again, a very, very important aspect, but a little confusing part is deductive reasoning. And this is something very basic, which every child should know. And this is the basis of the modern scientific principle. So so let's just take a couple of minutes to understand what deductive reasoning is all about. So let's have a sentence which says, if it rained, then the grass is wet. Okay. Now, this is just a sentence and there's a form to it. So it's if and then you can do a reasoning that if it rained, I mean, you have one input that it rained. Now you can say that the grass will be wet even without going out. We can say it rained. Now, if I walk out on my lawn, it is going to be slushy and there's going to be water. So this is reasoning from just one bit. You know the causation of what this will entail. So if I you're going to die. So if you fall down immediately, you'll know that you're going to die. So you can sort of infer it, and this is causal. So if you get corona, and this is what is going to happen next. Okay, you will have problem in breathing. So you can immediately infer that. But there are also wrong forms of this arguments, which are known as fallacies. So if you use the same knowledge base, which says if it rained, then the grass is wet, you cannot do reasoning in this manner that the grass is wet. When you find the grass wet and you just wake up in the morning, you find the grass wet, can you say that it has rained? Because you have this knowledge base which is saying that if it rains, if the grass will get wet. You cannot conclusively prove because the grass can get wet because of a number of other reasons. It could be just your sprinkler which is on, made the grass wet. It could be your pet dog which has gone and made the grass wet. You don't know, but the grass is wet. So this is something which we use in a normal day-to-day living. In politics, in religion, or in ideologies, we actually fall prey to this kind of reasoning. So this is known as fallacies. And so there are good forms and there are bad forms. Now, to do this explainable AI, you can understand the good forms and then you can explain it. If it's bad, you make a skyscraper and put rockets under it. Can I make it float? So then I can sort of tell you the reason why it cannot do that. You can't do that because a skyscraper is made of cement and all those things. You can always come up with reasoning, and there is causal reasoning. So now the best part of this was that we've understood that instead of sentences, you can use just symbols. So this is known as symbolic computation. You really don't have to know everything. Let's say data is encrypted and there's some encrypted communication taking place. Now, can you actually still compute say something is right or something is wrong? It happens that you can Q and I just replace P and Q with any kind of sentence, and now I have a system of computing mathematically. Using symbols and coming to a conclusion whether a particular theorem is correct or wrong. So this is very, very essential again. Where let's say if I hear terrorists talking about वो gift का packet वहाँ रख देंगे, that gift packet will be given to you. So over a period of time, if I get all the inputs, the facts, I can use symbolic computation. I can compute that what that packet is all about. It could be an IED, an explosive, or it could be a weapon. So I can sort of link up things and I can connect. And link up, I need to retain the valid arguments through formal methods. That's a very, very important aspect of AI, which needs to be enforced and deployed. So okay, so this is valid arguments. You can go back and surf online and check out what actually applies to you. You may be using maybe 3 or 4 of them in your daily life, and without knowing. And if you understand that, you can sort of cure yourself from that. And so in marketing, sales, politicians, religious gurus, all these people use this kind of arguments and get away with it. And the same thing will apply to you even in your day-to-day this thing in your domain, biomedical technologies. When you want to really understand if a particular medicine will cure a particular disease, so and sort of put in all the facts. And so if you look at collecting data, and always you can't do that. You can't learn through the process of induction always. You can't learn through experience always. It's a bad thing to learn through experience, because you can't experience everything. So for example, so there's a humorous take on suicide bombers. They can't learn through experience at all. They will have to learn through others' experience. So the better way to learn is formal methods, the deductive process, and that is what Einstein also used to understand E equals mc square, or understand general relativity theory, or people who predicted, the Bose was able to predict boson, because he didn't experience it, he didn't see it. He just used mathematics, he just used deductive logic to come to that conclusion. So in biomedical engineering as well, or any domain, you need to really start using those. If you don't use those, your systems will become unexplainable and also will be dangerous. So thought experiments and other things, all the science, what you see is all deductive processes. Right? When you do something in the lab, that is inductive process. But mostly you learn a lot through deductive process alone. So you can't do an experiment, or if you want to construct Albulch, you can't do an experiment, right? Because you have to build it. You can't build it and test it. So how are you sure that you can build such a tall story, and what is the model and which will actually make it successful? You use deductive logic, thought experiment, and through knowledge you build it. So that is very important, which you need to incorporate in your life. To have law for ROS, which is a AI tool or AI platform, which gives you that the facility to actually you don't have to go through all the policies and laws. Everything is loaded into the system, and it can tell you the output. So a lot of critical functions in law firms are getting replaced by AI, and it has to be correct. And in this case, it is exact. So, and it has to be explainable also. So if it is going to give a verdict to fight in the court, you really need to know why it has given those verdicts. And that is what ROS will help you do. And so you need explainable AI in order to, again, fight through this case. So we talked about Bayesian network. So similar to what we were talking about sentences. Now, if those sentences were all in probabilistic method. So let's say it is probable that it is going to rain just now, and it is probable that what is the probability if it rains, this particular area will get right. So how do you there's going to be a storm and you have to stop fishing, because you can't just throw it just like that. You have to explain why you can't fish, why it is going to stop. So you actually represent it in this kind of form, where you have nodes, they are connected to other this thing. So the grade happens because of intelligence, the grade happens because of difficulty of exam also. So the exam bad grades, intelligence is. Can you still hear me? Hello, can I get some response, please? I saw something in the internet
Yes,
connection.
sir.
Yes, sir. Yes, sir.
Yes, sir.
Okay, fine. So you can represent and model your space as a Bayesian network, and then you can evaluate. So let's say you get an evidence that a person is intelligent. Immediately you can say what kind of grade and letter he's going to get. Is he going to be in Alpha or Bravo? Now let's say you don't have any understanding about intelligence, but you and suddenly see the exam difficult. Know that what is the people will get is one,
Excuse
and
me,
you'll have
sir.
to
Excuse
expand
me, sir.
and to you'll have to beings to apply their mind. Therefore, it has to be modeled as a Bayesian network. Because if you have a particular gene, what is the probability that you will get cancer when you grow old? What is the probability that you will die because of so and so disease? So all these probabilities will have to be modeled, and so this is a particular model. And when you get one evidence that okay, this person is a smoker now, so now what is the probability that he could get cancer? Because he's got these genes also, and he's got this life habits. All of these are modeled into it, but the system will definitely tell you that you are prone to for cancer, but won't you like to know why it is telling you? So that is what is explainable AI. I mean, if you don't understand that, you cannot cure the problem. You'll only know that okay, you will get cancer, but then it can say okay, because you're living in this city, you're living in Delhi, and the pollution is very bad, and you also have a lung condition, so and then the genetics gene is there, so therefore you will get cancer. So now you know, okay, what can you do to cure that? I should move away from Delhi. Okay, so that is the best way to live, or I should quit smoking. So when you want to take some decisions and inference, you really have to understand the explanation behind it. Without that, you lose half the information, and you will take wrong decisions. And I'll give you an example also how these wrong decisions get into a catastrophic event. So other things are like fuzzy logic. When you have other uncertainties of Bayesian network is about event based uncertainty. You have it or you don't. You have the gene or you don't have the gene, and if you are a smoker or not smoker. But fuzzy logic is about maybe or maybe not kind of thing. So if somebody is talking about red color, you really don't know what is red color. Somebody is talking, saying that the weather is cold today. Now, for a Russian, it means that it's minus 10 degrees. But for a guy from Madras, it means it's 25 degrees. So cold means the same thing for both. But so therefore, you have to model it in the fuzzy world, and you have to use it. Again, when you compute, it has to really give out the reason why it has come up with this kind of this thing. So let's say a air conditioning system is there. Why is the air conditioning switching on right now? So it has to have an explanation for that. So if somebody is sitting in an industrial floor or even in biomedical engineering, if you're looking at inputs from your wearable device coming in, and it is telling you that something is switching on or switching off, you have to know why it is happening. And if there is some other inputs to it, because there are always exceptions, then you can respond to it. So for example, you have this people who have fits, they've got implants in their brain, and whenever those kind of fits, the signals come up, so they can predict that he's going to have a fit right now, I mean an attack, and before that it can preempt a particular signal which will subside that, so therefore he's safe. So a guy may be driving his car and suddenly if he gets fits, he's going to meet with an accident. So your brain, and if you've used AI models, save yourself. But if you also need to know that why it has happened, right? So when you do the diagnostics and things like that, you have to have an understanding there as well. And there is also ignorance, the amount of ignorance. So if you really don't know 90% of a particular case, you just have 10% evidence. With that, you cannot say a person is really the murderer or not. You can't say a particular candidate is the reason for this disease or not. You have to have better information. But so when you, depending upon the ignorance levels, your decisions will change. So if somebody's told you if it's raining and it just tells you that you need to slow down your car, I mean, you have to, obviously, it's a skid. In a particular case, it is asking you to speed up. Maybe because of the condition of the road is good, and maybe if you speed up, you will cross the system, the signal, storm system. That's better for you. So it all ignorant really don't know that whether it is going to be really bad storm. So it can also tell you to stop by the road, right? And so something like that, I mean, is used in Navy. If the ship has to go out or it should stay in the harbor, what is the best thing for it? And you have to understand why system prompting to do such a thing. And also when they're evolving, okay, you have bacteria which is evolving. So your medicine also needs to actually, the approach to actually defeat that will have to go through game theory system. So it's a multi-agent system where others are responding, and maybe if you're in an isolated situation, if you're trying to defeat a particular I mean bacteria, kill a particular bacteria, it may be good. But if you apply it inside a human body, then you have other systems which are get or operation. So those kind of things you'll have to understand in a multi-agent system. How do we, behave? So if you look at India and were just the only world we would have defeated Pakistan nation system, and we are tied up in trade and so on and so forth. So it's very difficult. It's not just not very simple and straightforward, and therefore when the system uses game theory and tells you that you need to do this is the step you need to do, like for example in a chess game you need to move the pawn. You may say, I mean, that's a stupid move. I mean, it's very counterintuitive. Why should I move the pawn? It doesn't. So then the system should be able to say, see, if you move this pawn, that guy will have to move the horse only, and thereafter, then you can move the king and you can defeat it. So it gives you the explanation behind it, behind such kind of platforms where multi-agent systems are. So in all this, again, another thing which you need to understand is which algorithm to use in which context. So you'll have Bayesian networks, you will have different, and there is always a context nature to the solution. So therefore, you need to find the computational cost of that technology, and so that also is a part of the system should be able to tell you that at present this is the kind of thought process or algorithm which is actually running behind their machines and systems. So there is something known as AI effect. If you look at the programs, it all converts into algorithm, right? There is an algorithm which is always running, and if you understand the algorithm, you can build a very good marketing system, and the sales people really understand these things very well. So, so ultimately, everything boils down to mathematics and some computation. So this is known as AI effect. It's like a rainbow. From far away, it looks very intelligent. When you just go close to it, it disappears into a mathematical algorithm. And so it looks like this. In the brain, it looks like this, right? It's just neurons. It's all data, and you manipulate and you get some output. You want things to be intelligent. If you're making a shoe, it has to be intelligent. You have to use something intelligent. It is not good to start searching from one corner to the other corner. You do indexing, and then you can sort things, and you can display it in different sections. It makes your life much more easier. So in every aspect, AI is being used. And when you look at the brain, it actually you can create a brain as big as a planet, artificial brain. But a human brain has got limitations. So you have something known as Prism, and you have things like DeepMind. So Snowden actually Prism, where US was using the entire world's data on the internet and elsewhere. The open source intelligence was being used for trade, for defense, and for intelligence purposes. So you can build it as big as possible. But when you come to building robotic arms and other parts, they have made quite amount of progress. But this is something which is very difficult, not because of uh, things about intelligence. It's about how to translate it in nanotechnology. When you look at fingers, we have millions of cells which has got it can sense and it can react, respond. So the dexterity and that precision is there. But when you this thing, it's under development, it's under R&D. But yes, in an industrial setting, it's doing extremely well. So embodied computation is something is challenging, and where there is a lot of AI work and machine learning algorithms, understanding, because your arm and your cognitive abilities will have to understand why it has to do a particular thing. So if it understands a floor is going to be slippery, your leg movements will be altered accordingly. Otherwise, if it's going to use the same movement for all surface, you're going to fall. We do it very intuitively because we've evolved such process. So when we replace humans from systems, we have aircrafts without pilots. So it gives you a lot of benefits, like avionics goes and life support system goes away, your crew safety. I mean, basically the metal plate aircraft goes away. It becomes lighter. You can carry more away. I mean, a system just has to be trained once, and it is loaded. It will not forget. Human beings forget, and there's logistics problem, fatigue. You have nuclear biological scenarios, casualty evacuation, disabilities, high quality. So I'm just relating this to the armed forces as well and national security. You are political in this environment. You'll be answerable if you kill human beings. But robots, you can generate hundreds, and and also it makes good financial sense because of all this. Aircrafts, you have autopilots. The pilots are going away, but what is not going away? You can't aerostat the ground, because that is the kind of work which we do. Is so automating that is going to be an issue, and till nanotechnology and others catch up, it's going to be an issue. So this is known as Moravec's paradox, where we say that the brain can be replaced faster than the body, and also in a factory, I mean, in the industry, the CEO can be replaced faster than the actual peon. I mean, the peon, you cannot do away with the peon, but you can sort of do away with the, the decision makers. And when you look at, healthcare, so you have robotics, surgeons, and these are very, very precise, right? So if you get operated through a surgical robot, you can move out of the hospital the same day in a few hours. But if the same thing is done by human beings, then it's not a very precise work. You need more recuperation. And also, once you make a surgical robot like this, you can just multiply it. Whereas if you for doctors, it'll take them 5 years and 8 years to actually become that expert. And that is an issue. Here, you can just scale it up the same day. So if there's a disaster, if you can manufacture them en masse, you can manufacture and deploy them. So that's happening is just a small example of how it is affecting healthcare. And so the scope in biomedical engineering, you have tremendous, uh, verticals which are emerging. And we are not getting into all that, and we are not looking at the applications and all that. It applies to all these domains. AI. We are just looking at another, I think, 20 minutes, so we are good to go. So in all of this, so when the domain expertise and domain knowledge itself is expanding, there's an overload of information, and then it's very difficult for us to make the meaning out of it. And more, it gets more and more. We'll have to continuously get themselves trained. Now, all of a sudden, you have cybersecurity coming in, so they'll have to understand cybersecurity as well. And then you have, data privacy laws which are coming in, which are the compliances are very complex. Now, again, doctors will have to learn that as also. And it's a never-ending process. It becomes very difficult if it is done manually. So you need to actually look into automated systems And when you automate a system without explanation, then you will have accidents like this. So you have this Lion Air crash, right? 737 Max. It had an automated system to actually enable the aircraft to keep flying, but the pilots didn't understand that. So there was no mechanism which was explaining what was happening, and therefore the accidents took place. Pilots didn't understand; they were giving the wrong inputs, and the aircraft crashed. So we had a couple of events like this, and the similar thing would happen if we use AI without explainable component in it. And when we look at healthcare, it can be disastrous for a human being, right? So it's again life-threatening, which is a critical system, and you really need to know. So right now we have let's see what kind of systems we have. We have a huge amount of data, so obviously we work with big data, and it's unstructured. So you have images, you will have X-ray sheets and things like that. So it's an unstructured data essentially, and you need to do analytics on it. You need to do streaming data analytics, which is real-time analytics, and then you can do historic analytics, which will capture the trends of this thing. So both are required even in healthcare. And so essentially, whether it's IoT in healthcare or IoT in the industry, industrial IoT, or in home automation, it is the same pipeline, and the infrastructure is almost the same. So you have servers which where you have the big data analytics, big data platforms like Hadoop, or you can have microservices or Kubernetes based containers which are used to actually handle huge amount of data and huge amount of computation. Once it is done, it has to be actually fed to the human operators who will take further decisions. So it augments the human operation. So even in healthcare, your system should really tell you that what's happening with your patients and your clients. So you should have diagnostic capability. You should have predictive capability of saying that okay, you will come in for diabetes, when you age 45. So when you have predictions, when predictions are possible, you can also prescribe. So you can say, okay, from now itself, you start, taking these tablets, or you need to reduce the sugar levels and things like that. So, so you can sort of prescribe even before an event occurs, even before a catastrophic event occurs, even before you have an heart attack, something like that. So the dashboard has to be intuitive, and it's not that everybody gets all information within. So if you go to a ENT specialist, you should be getting information about you, because about the ears and nose. So he would also, and there will be a certain component of the nature that you're diabetic and you have so and so other features. So accordingly, you can prescribe. So every doctor or every individual operator or manager will have different requirement from this entire system. So he must be fed only his relevant information. So that is functional and role-based information dissemination. Also, you have to. It also has to have a temporal component to it on a time basis. So you say, okay, right now he requires this. Right now you need to stop doing this. So it should be understand that what you need to do when you need to do it. So for example, right now it can tell me that okay, you need to take some energy drink because your energy level is going low. And in the next moment, it could be that okay, you need to now sleep. It's been a long time. So I mean, the information should be thrown at the right time to the right person, the right manner, so that he can understand. And also, it is customized. So, for example, if a housewife comes and looks at the dashboard, it should be able to respond to it in that manner, so that and if a professional comes to the picture, he will get can throw information at you. So what are the issues with this thing, the present method without explainable AI? Well, you lack transparency. You have, I mean, the model is not generalized enough. So whatever it has learned, it's learned in a very small, narrow field, and therefore exceptions and other things it will not be able to classify well. Absence of casual reasoning. So without the inferencing mechanisms, you will miss out on the causal reasoning. What causes what? So that reasoning must be there through Bayesian networks or through your logic system. A part of these difficulties are, so this is just one of the example. I mean, it creates a black box kind of situation when you use deep learning models, and there are so many parameters. So you really need to understand why the system is telling you this, and because of which parameter what is happening. Probably you can also tune in your parameters, or you can take that kind of precaution, and you can respond to it again contextually, so with information. So explainability, transparency, and also provability. We've seen some of the tools which can be used in AI to do all of this. Provability, for example, I mean, we are talking about symbolic computation and things like that, and also through data you can prove by the null hypothesis testing. Okay, and yeah, if you can map up the entire model, then the transparency also comes in, and you can explain with that. So the goal of explainable AI, another example of suppose if your system is trained to recognize cats, so the first layer, this thing top layer is what we are using right now. But what we need is we need the system also to tell us why it has termed it as cat, because it has got a fur and it's got whiskers and claws. So there are reasons which are given, and so it needs to understand that, and then that is more believable, and it's better. So the aim of explainable AI, which is also known as XAI, is basically to address these problems. I mean, it may be in prediction models, predictive models, or diagnostic models. It can be in any sense. It can be deep learning models. Okay. So depending upon the non-linearity and depending upon the complexity, you can have uh, either you can go in for just ANN or deep learning models, and you can use Bayesian modeling systems. So we have gone through the tools and the solutions what you can use there as well. So that is the entire aim of this explainable AI. And what is the utility part of it? What does the user want? He wants to find out how errors are taking place. He wants to find out how much he can trust this. If somebody is, if the system is telling you that this guy is a terrorist, so what is the percentage it has identified the face? Maybe it is 60% or is it 90%? And then depending on that, you can take a call whether you need to arrest him or kill him or what you need. The similar thing is what doctors also will be dealing with. If a system is telling you that this person has got cancer, so how does it? How did the system come to that conclusion? It can be a wrong diagnostics also, and so before administrating medicines and things like that, you have to ascertain uh, what the system is throwing is correct and why it is saying so. So this all this is included, should be included in the development process only when you engineer something for healthcare. So in engineering, maybe it's hardware, software with life cells. Have to incorporate explainable AI in the development stage itself, not retrofit it later, which will not happen properly. So you need to create understandable AI, you need to create transparent AI, and you need to create impactful AI. Because of that explanation, you should be able to understand the process well. Because of the explanation, you have greater transparency of what is happening underneath in the computation and what you need to do. How do you respond? So that comes from the impactful AI part of it. And in the implementation stage, you need to convert all this into mathematical models, and you need to create those kind of interfaces depending upon the contextual nature of the person who's consuming it. So, for example, when cars understands when you are driving a car and when your brother or your wife is driving a car. Everyone has their own way of applying the brake, but these cars also have anti-braking systems, which is a computer-based system which doesn't allow the car to skid even if you jam the brakes. So depending upon how a person is applying the brakes, it understands the entities. It does clustering. It understands there are three people driving this car, and today this person is driving the car. So when he's giving this input, that means this is what I need to do. So explainable model and explainable interface needs to be given. And in the deployment stage, you need to train, you need to use the critical thinking loop. You need to correct the systems, okay, ask questions. You have to look at the quality assurance, and you need to test it, monitor, debug, and then put it into the system. And then you can host these services on the clouds, or you can do it on premise, or you can also be on the edge where you're using some biomedical system or device. They can be embedded into these models can be embedded into those devices as well, and so that's how you finally deploy it and use the services on the cloud. So there are other aspects to AI which can be used. So you have the to the machine, then have better understanding. The same things are being used even for medical operations and teaching purposes. If you want to design a particular wearable device or implant device, you can use these equipment to have better understanding. So you have wearable devices, you have implant devices. Now we are talking about implanting, neural link also. So besides this, you have DevSecOps, which is development operations, including security. So the security has to be embedded right there, because healthcare has got HIPAA compliance and other compliances which are very, very stringent. So you can't lose data. You can't allow others to hack into somebody's pacemaker and kill him, which can be done. So you need to be very these devices, and therefore the security aspect also needs to be plugged into the development stage itself. And so along with the operations, the development is created along with the security in place. And the GRC is all governance, risk, and compliances. So you have to be aware of all the policies and compliances when you actually build these devices. And so they will have to be made so that the compliances are met. These are cannot again be, you can't retrofit it later, which will cost you a lot, and it will not work well. You need to do it when you develop it at the first stage. So in the cybersecurity side, you need to do the vulnerability assessment of your own devices and your own systems, your own AI systems. And also you have to look into the threat intelligence part of what is happening in the world, how other systems are getting hacked, how these and there's a huge AI war going on there as well. So the bots are also AI driven. They are intelligent. They know how to hide. They know how to masquerade as something else and harm the system. And also the antivirus and your security products are also becoming more and more intelligent. So they are also, so there's a cat and mouse game going on where AI is involved. And again, it has to be explainable. I mean, if the system is saying shut down immediately because there is an attack, you have to know what kind of attack, from where it is coming. So you need some understanding of what is going on. Otherwise, the orchestration and response automation system will again create situations like 737 Max, where the system is trying to help you, but you are, maybe there's an operation going on and then the system is shutting off. You feel that it may harm the patient, but at the same time, if it is on, probably there is a malicious actor who's taken charge of it. He can kill the patient. So there again, you need to understand why the system is doing something like this, so that it's better to switch it off and then handle the patient manually rather than trying to fight the system. So in the army, actually, I was involved in all these, AI labs where we had the swarm robots, and essentially it is all. You can replace this with a medical device, and it's the same this thing output which you get. So we had made about 32 swarm systems, and these are all driverless cars. Again, it can speak to you, it can talk to you, it can fire on its own without a driver on board, weapon-mounted platform. So there are plenty of robotic systems. Here, this is a hexacopter, and then you can see a wearable device which I'm wearing, and so this is something which is also essential for in medical world and in healthcare. So in the wearable device, it can actually give you a 32-inch screen at 7 feet distance whenever you want to look at it. So it's actually, there's an iris scan there, and when you want to see this, it comes up. So you can get contextual information when you're operating, or when you're when you are practicing your you may be a general practitioner or a specialist, and when you look at a patient, you can get all his records there, so it can be on the fly. So these are some of the geo systems. So I mean, again, technical demonstrations. GIS applications, again, these can be used to study what kind of pathological effects are you having in different location based responses, what kind of pandemic is happening where. So all these can be on the GIS platform, and you can use game theory and other things. So everything sort of plugs in. Similarly, even in biomedical engineering, so this is a remote presence robot. Again, you can use it for telemedicine. You also have app-based this thing systems, mobile app-based systems, where you have responders, and for elderly care, you create these systems where you can find out if somebody is fallen down in it or not, right? So now the system can be camera-based or wearable device-based, but it also has to differentiate whether this individual is doing yoga or has he fallen down. So it should not put an alarm and create responses in ambulances and other medical facilities just because he's doing some push up or he's on the ground. So it has to differentiate. So you need to explain, if he's down, so why is he down, right? So for that you need you have a lot of ways of inferring that. So these are kind of dashboards which can give you the human interface from the machines to the human being. Again, IoT integration and all this is part of that. Predictive maintenance. So this is maybe for an aircraft, but it's the same thing which happens in healthcare as well. And so we have this thing. That is what essentially we are working on right now. So I have a partner in Thailand. So we are working on diagnostics of basically the well. We are working on a wellness program. So how do you understand if a person is becoming happy by doing a particular activity? What does he need to do? And also we have another program for healthcare, as I said, I mean for elderly care, to understand if the person is in some harm, or is he okay? Is he having a heart attack or something like that? So these can be predicted, early warnings can be given, and then he can be saved, because most of these old people are living alone now. So the same thing applies even in agricultural, the same yield prediction, okay, in other defense systems, in healthcare. So you can have a complete platform where all kinds of entities and agents can derive benefits out of it. So you can have the insurance guys, the administrators, you can have the developers, the ICT guy, the doctors, the patients, all of them using the same kind of platform. And using AI, they can actually find their solutions for their respective job. And also along with it, they need to find the explanations behind these. So one of a very good way of creating interface is creating chatbots where you can do contextual querying. Instead of clicking and surfing through, it takes a long time. You can directly ask questions, and these things can respond. So these are NLP based systems. So these are some of the systems we are working on again, and you can create as a better system as you want. And when you have a huge knowledge base, I think this is the way forward. And also, if you want to store information in distributed ledgers, and if you want non-repudiation, and if you want to really uh, have reliability, if you want reliability that the data will be there forever, so you can use blockchains. That's a good way of storing. So this is, again, if you're storing information about land parcels, or if you're storing information about personal data, the same thing. Essentially, you can start storing healthcare details also there. And right now, since the compliances are really uh, stringent, so I think blockchain will give you a good dividend. So when you talk about, you also have the HR component, which doctors should be placed where, which doctor should look at what systems, how do you actually choose people, how do you choose the best job applicant to the kind of job. So this will apply even in biomedical engineering. You can also use similar things for, I mean, making a choice of your insurer or making a choice of your healthcare agency and things like that. And also it gives you a better way of let's say that there are some specialists here, and in case a particular hospital doesn't have that specialist and there's a life threatening situation, so you can quickly sort of take those services. So it's all going to go into the cloud, and there will be sharing. I mean, you will be sharing systems like that. So a few slides about what we do. So we are now, I mean, as I said, it's actually the biodata says two, but right now we have around 6 engineering colleges where we are managing the AI and cyber lab, and we are also training them. We are setting up the HPC systems, the high computing systems. Uh, and also we are engaged in creating online courses, like for Grant Thornton we are creating cybersecurity courses and other courses. We also do take up seminars and workshops in these, and so we have been selected by the Mauritian government also to train their officials. So seminars and workshops are something which we are always engaged in. It gives you a better platform for integration and networking. And finally, AI is all about you need the art of integration. How can you put in different things? So it is something like that Three Idiot movie, where I mean, if you can make do with a pencil, it is good instead of creating $1 million pen. So we don't have to look at the complexity. That is not what is AI. AI is all about how can you reduce the complexity and do the job. So if you don't understand that, you may be spending a lot of AI technologies in your devices, in your systems, and it will all look like this ladder in which this man is trying to climb up, which is not the way to do AI. So with that, I've come to the end of my session. I hope this thing I've given you certain inputs which has expanded your knowledge on this subject. And so more than AI, I think I hope that I was explainable. What I'm talking about was explainable. In case if there are any doubts, I can explain it some more. Thank you.
Thank you, sir. Sir, we have some few questions from participants.
Yeah.
So shall we continue, sir?
Yeah, yes, ma'am.
First question is how optimization plays important role in machine learning.
Okay. How optimization plays an important role in machine learning. So when you talk about optimization, there are different processes in machine learning. One is just to create the model itself, optimizing your weights so that the model accurately captures the relationship between the attributes. So when we talked about the house and the size of the house and the cost of the house, that line which came up, the knowledge, there will be a mathematical formula to it. So when we try to discover that line through neural networks, it becomes very, very difficult, and the line may not be really accurate. So depending upon your algorithms, depending upon your parameter tuning, the line can be little off, left or right, and may not represent it, in the best sense. And instead of a line, probably you can have a thick space which will give you some kind of a generalized space. So how well your model captures that space is all in the optimization space. So that is one place where you use better gradient descent methods and other methods, parameter tuning and things like that, and try to get the best fit for your model. The second this thing is in the inference part of it. So once you get the output from this machine learning models, what kind of inferences you need to take. So for example, it all depends on your ignorance also. Let's say I'm sitting in a forest and suddenly I find something slithering behind me. So I have to jump out, right? Because I know there could be a snake. So it is contextual. But tomorrow, if I'm sitting in cafe coffee day or something, and something is behind me like a rope, I don't have to jump, because there the inference is like I can see there is something like a rope. Even in the forest, I saw something like a rope, but there I could infer that it could be a snake, and that therefore I take a different decision. But in cafe coffee day, I know that you can't have a snake there, so I feel that it could be a rope. So the inference mechanism also, you need to choose the best inference mechanism to optimize your output. And there you can use an ensemble method to actually get an output, and then your inference logic mechanisms to get the best output. So you can optimize there as well. And also another thing is when you can look at the data. When you feed in the data, you send in clean data and better labeled data. So, and also the sample size. If the sample size is too less, then you may have a overfitted model. You got to have a large sample space to generalize the model so that you get a thick space. Because everywhere, 2-bedroom flat will not be 20 lakh. It may be a little bit 25 also you may get for 15 also. So there's a space. It is not just a line. Yeah. So the next question.
Okay, sir. What is difference between optimization and regression?
Optimization and regression. See, regression is nothing but it is a relationship between two different attributes or two or more attributes, right? It's the relationship between, let's say, if there is the temperature falls down, the this thing of cold cases of cold goes up. So this is a regression curve. Optimization is how well can you actually how well a system works. Maybe it's in the inference space. So if you're talking about how good is the line, which tells me that if it is 20 degrees, then what is the case? This thing, how much case there could be? If it becomes 23 degrees, what will be the case? So is there a very accurate predictive curve which can tell me that if the temperature of the uh, ocean increases by 1 degree, what will happen to the coral this thing? So is my prediction that regression curve, how well it is? So if you can optimize that, so it could mean many things, right? So as I said, so it can be the model optimization, it could be the inference mechanism optimization, or it could be the data input optimization. So optimization is all about the best result. Regression is a relationship between attributes. Yeah.
One more question, sir. Kindly suggest any resources such as books, tutorials, and websites for design and development of embedded hardware for building the drone systems.
Okay, so embedded hardware, you wanted, resources online, right?
Yes, yes.
Yeah, so I mean, there are plenty. I mean, I can't recommend anything as such, but right now I can sort of share it on a mail kind of thing because there are plenty there. So depending upon what kind of embedded systems you're working with, so are you working with edge computing where you want,
Sir, for drone system.
Pardon me?
For drone systems, sir.
For
Embedded
drone system.
hardware. Yes.
Okay, so for drone systems, see, the best this thing is in IIT Kanpur and IIT Chennai. They have some incubation there, and they have some startups. They are good because that is something which is going to be indigenous. Uh, Most of the drones are all assembled because what is there in a drone? You have the structure, you have the rotors, brushless motors, and you have controller, flight controller, and that software which is driving that, and an autopilot. So all these are actually manufactured outside India. In India, we don't have such kind of embedded systems right now. We are using the embedded system which is already there. Like IIT Chennai is now working on its own embedded system. But again, since we don't manufacture chips here in India, the form factor will be high, and yeah, we need to actually start manufacturing chips here. That's very important. And also to come up with a flight controller and all that, it takes about 2 to 3 years. People have been using whatever open source which was available, or they've been buying it from vendors and OEMs. So, so for drones, you will have very good YouTube videos. You may have Coursera and Udemy also is there. And so online, you just need to know how to surf. So right now, I think you need to learn how to catch a fish rather than me pointing you to a fish. So you will find very good resources there. So all you need to do is learn how to use open source intelligence, how to investigate, and it will take you deeper and deeper into the best resources available there.
Okay, sir. Sir, one more question. Is there any simulation tool available for testing of drone system prior to its hardware implementation?
Yeah, so you have the mission planner and all that is already available, and so you can use those itself for simulation by manipulating the inputs. So if you can this thing get the input data input stream, and then you can look at the output of what it's going to do. Apart from that, you can also use platforms like Unity 3D and those big gaming platforms where these simulations can be again used. For automobile, you have very good simulators available, and so for drones also you will get numerous simulators which are being used. So depending upon whether it's open source you want or you want to purchase it, so or at times depending upon your development you can develop it yourself also. So I think for the dynamics part or for the navigation part, whatever you want to simulate, these systems are already available in online resources.
Okay, thank you, sir.
Yeah.
Now I will call Dr. Swati Bisikar for vote of thanks.
Thank you, ma'am.
Thank you, ma'am. Thank you, sir, for excellent session. Good afternoon, one and all. On behalf of JSPM's Rajarshi Shahu College of Engineering, Department of ENTC, I, Dr. Swati Bisikar, take this privilege to propose vote of thanks for today's eminent speaker, Colonel P.J. Anand Kumar, sir. Sir, your session was very informative as well as interactive and interesting, sir. So you have explored the various areas for carrying out the research in AI as well as in biomedical and the other aspects like machine learning and everything. Sir. Thank you very much. I'm sure that the participants are greatly benefited by your talk. We are really enlightened with your knowledge and presence, sir. Thank you very much for sparing your valuable time. Thanks a lot.
Thank you, ma'am. Thanks a lot.
Yes. Thank you, sir, for coming here and sparing your valuable time once again. Dear participants, tomorrow there will be a session at 10 a.m. sharp, and it will start at 10 a.m. and the valedictory session for the FDP will be at 11:30 sharp. Okay. So with this, we will end this meeting today. Vibhuti madam, you can end the meeting. Yeah.